Hello everyone, and welcome to our session on arrays. Today, we'll be exploring what arrays are and why they are so important in programming. We'll introduce the core concepts behind arrays and set the stage for how these data structures form the foundation for more advanced topics in data structures and algorithms. Let's start with the basics. An array is a data structure that stores a collection of elements, typically all of the same data type. Arrays can be either fixed in size, where the size is predetermined, or dynamic, allowing the size to change during runtime. One of their key characteristics is that elements are accessible via indices, making it easy to retrieve or update data. On this slide, you'll see a visual diagram that illustrates an array structure with labeled indices to help visualize this concept. Now, why do we use arrays? Arrays provide an efficient way to organize data because they offer efficient data organization, a systematic way to store and access sequences of data. Fast access, direct access using numerical indices, which gives constant time access to any element. Memory management, arrays facilitate contiguous memory allocation, which can optimize cache usage. They are commonly used for storing lists of data such as numbers, characters, or even objects. On this slide, you can refer to the visual demonstration comparing unordered data storage with array-based storage to see how much more organized and efficient arrays can be. In programming, arrays come in two main flavors, static and dynamic. Static arrays have a fixed size that is allocated at compile time, as seen in languages like C or C++. Dynamic arrays can resize at runtime and are common in languages such as Python and Java, where, for example, Python lists or Java array lists provide more flexibility. To illustrate this, I've included side-by-side code snippets from C, Python, and Java that demonstrate how arrays are declared and used in different languages. Let's discuss some common operations you can perform with arrays. Initialization, declaring an array and assigning initial values. Traversal, iterating over the array elements using loops. Insertion and deletion, these operations can differ between static and dynamic arrays. Static arrays typically have fixed sizes, while dynamic arrays can adjust. Search and sort, basic algorithms to locate or order elements within an array. It's also important to understand memory considerations, such as array bounds and potential pitfalls like buffer overflow. These operations form the backbone of many programming tasks. In this section, we'll focus on practical techniques for working with arrays. Indexing, how to access and update elements using their indices. Iteration methods, various ways to loop through arrays, whether through for loops, while loops, or even recursion, depending on the language. Slicing and dicing, utilizing language-specific features to extract subarrays. For example, Python's list slicing is a very powerful tool. A short animation on this slide demonstrates an algorithm traversing an array, which should help solidify your understanding of these manipulation techniques. Now, let's go over some best practices when working with arrays. Memory efficiency, always choose the correct type and size for your arrays to prevent memory wastage. Error handling, it's crucial to safeguard against out-of-bound indices and invalid operations. Performance optimization, consider factors like cache locality and language-specific optimizations, especially when working with large data sets. Comparison with other data structures, understand when arrays are the best choice compared to other structures like linked lists or trees. These guidelines are key for writing efficient, maintainable code. To summarize, arrays are a foundational data structure that enables efficient storage and retrieval of data. They are essential for building more complex algorithms and data structures. As we've discussed today, arrays can be fixed in size or dynamic, each with its own strengths and trade-offs. Understanding array operations and manipulation techniques is critical for optimizing performance. Best practices help you maximize efficiency and avoid common pitfalls. Going forward, I encourage you to explore array implementations in your preferred programming language and practice these concepts through hands-on exercises. Now, let's move on to the Q&A session. Before we conclude, let's quickly recap the visual demonstrations from today. We saw a diagram of an array structure with index labels. We compared code snippets for arrays in different programming languages. And we watched an animation showing an algorithm traversing an array. These visuals are designed to deepen your understanding and improve your practical skills when working with arrays. Thank you for joining this session. On this note, I am stopping over here. See you in the next session.